I'm a researcher and a software engineer, and my role is an applications side of the DRES project. So this is about providing distributed energy resilience, grid resilience during extreme weather events using electric vehicles. Our other colleagues on this project are, so Dessin Curley is also at Edinburgh, she's unavailable today of course, and Liz Sotu, who's leading this project as well from Bath. Kilo will talk briefly at the end on some of the technical aspects of the project. And what this project is focusing on, what the main challenge is grid resilience during storms. So the issues obviously are huge. In 2022, in February, if you remember, we had three very large storm systems that hit the UK. This resulted in over 1 million homes losing their power, and obviously a lot of non-residential loads were also lost in those regions to devastating effect. There's a second issue that sort of underlines that sort of sets the background of this project as well, which is the one of electric vehicles on the grid. The issues around the stress that they bring to the network and so on is a very widely studied topic, and we're not addressing that general challenge here. But in terms of the extreme weather events and the impact that EVs bring to the network, that's very much part of our focus. We're actually turning it into an opportunity and using the ethos of what DAFNI is about in integrating these two systems to see what opportunities might be there to actually introduce resilience to the grid through distributed energy resources that are dispatchable. So on the slide, there's two maps that show the background context of the kind of things that we think about. So we've got the climate risk, a measure of this on the left, and the EV infrastructure is shown here as well, the density of chargers for public EV points. Now, we understand, of course, that unmanaged charging of EV assets throughout the country brings a challenge to the network, and especially this is the case during storms. But the aim of the DRES project is to try and stimulate and coordinate and not compromise the integration of EV infrastructure with planning for extreme weather events. Part of the, many stakeholders are involved in this. The issues that are sensitive to this idea, including obviously the network operators, but the public see the full front of these storm events. And we look to try and introduce mechanisms that they can try and participate going forward in the future. So this is a technical feasibility. There are more aspects to do with markets and so on that would follow on from other ideas in the future. But this is a technical feasibility using optimization on the DAFNI platform. So the network operators have a number of mechanisms that they can use to manage and mitigate faults that occur through the network. And these include things like time of use tariffs, where the customer, the end use customer has a different tariff that we would pay or potentially be paid if they're importing or exporting to the grid. We have frequency services and short-term operating reserves, and black start, and so on. Our focus, as mentioned, is extreme weather, and what we need is a characterization of the system to be able to instigate these services. So we have signals that would then map towards services that would actually provide, that would make a difference on the network. So we have scenarios for business as usual, and during an extreme weather event, we have a scenario for before the event, during event, and post-event to schedule EV charging. And so smart chargers for EV, so we can drop loads and so on, and we can introduce vehicle-to-grid services as well through the scheme. Now, the externalities obviously are the starting point for all of this, and the two main ones are the weather. Is the weather normal? Is it volatile? And we need EV assets to be connected to the grid to be able to use them as an asset, of course, as well. So these are externalities. And what needs to happen, of course, is to map these across, and this is really what the DRES model, the DRES project is delivering this model as one of its key deliverables. So this, when detailed out fully, maps these different components to externalities, to signals, to services, to a wider picture, which is our DRES workflow. So this model just describes it's alongside a network flow model, and these are well-established types of models. They take considerable work to build from a data point of view, and we have a case study that we're using from a previous project, or a related project, using PIPSA, so Python Power Systems Analysis tool, and our case study is on Orkney, which is we often think of it as a bit of a microcosm to the UK system, where they have very high renewable capacity, install capacity. It's almost as high, I think, as the demand. There is extreme weather, certainly up there. It's in the very far north of Scotland. And there's actually a very high uptake of electric vehicles as well. So it's a model almost for a small UK microcosm of the network. This is one of our workflow approaches that we're looking at, which is clearly serial. In our testing scenarios, we're testing the scheduling sequencing of EV smart charging and vehicle to grid. But in the final deployment of what we'll have on DAFNI in the final stages will most likely be a parallel type of model. We'll also look at the potential of integrating weather as a model component as well in the wider system, so that'll bring a third component. And clearly data is the sort of basis for the context that sets what we're studying, which is a case study in the UK for rollout across a much wider area. So as the applications role that I take up in this project, one of the things I get quite involved with is trying to establish this delineation between models and workflows. In some environments in software development, in a commercial setting, this would be quite clear that you make general purpose code and models and so on that can be applied in other circumstances. But in research, it's quite often those lines are a bit blurred. That's not always a guarantee that you'll get delineation between the context that describes a specific scenario and a generalized model as well. So ultimately, it usually means that there's hard-coded context that's right throughout the code, which I think was a recognised problem for many people here. So one of the things that we're really working on is building this scheme so that we have static context files that describe the specifics, and we don't have context laced throughout the code. We can make plug-and-play models where we can change the basis of the model is the data and the parameters that go in, and it's not the source code. When you work with DAFNI, this comes to the fore very quickly, so it's quite comforting to see these things that are very important for good software design are almost encouraged through the use of DAFNI, part of the ethos. So part of our work, building parser tools and testing frameworks and so on, and generalized enhanced visualization so that we can test this, not just for our case study, but for different ones. And other people can do this hopefully in the future for us using our work. Again, plug and play concept is definitely, if you move to the slide before. And then another aspect to this, of course, and we believe is part of the DAFNI ethos, is the use of our data should be readily accepted into future models that we don't know about yet. We need to make sure that our outputs are generated in a way that they are reusable for processes that we don't envisage yet in the future. So I'll pass on just to Kilua.
I'm Kila. Now I'm talking about our project background and progress. For now, we can see this each of 3 stages that our distribution power network experience this. It will affect our people's lives and urban important load and the productions of factories. So we are trying to use electric vehicles to mitigate this effect. We can see that electric vehicles has developed very rapidly in recent years, and they have lots of idle time that we can use to serve electric power network by charging and discharging behaviors. So in our project, we are trying to use the electric vehicle to mitigate the impacts of extreme weather events on distribution network. On the bottom left is our a small experiment for the optimal schedule strategies. The left diagrams is 24 hours in network voltages. That is the normal situations. That means we don't hit any measures to control our electric vehicles. And the right diagrams is we use the optimal strategies to control electrical vehicles charging and discharging, and we assume that the extreme weather events happened at 10 o'clock. So we can see the left diagrams, the voltages from 10 o'clock become decreased significantly, and the extreme weather events will last 4 hours. And the right diagrams, it is used the optimal strategies to control electric vehicles. So we can see the voltages still decrease. That's because during the extreme weather events, it will have loads in our distribution network, but the voltages not have big waves. And the left diagrams, the lowest voltage values is around 0.9, but the right diagrams, the lowest voltages is around 0.92. So these experiments show that electric vehicles play an important role in the extreme weather events. So we try to use the similar strategies to control electric vehicles and develop optimal control strategies under the extreme weather events to serve the distribution power network. Finally, our objective to try to achieve the better voltage qualities and serve the energy bills. And that's all. Thank you.